I am Mr. Taru. In this video, we're going to strengthen our knowledge and skills of using the sigma notation or summations. We're also going to combine that with the idea of limits, which we've studied in the beginning of calculus now, to find the area of a plane within a region. Specifically with the two examples I do in the next video, we're going to be finding, for the first time ever, the area between the x-axis and the graph that a function makes between two boundaries of x, a and b, a lower and upper boundary. That's the second key problem that we learned in the beginning of calculus. The first was doing derivatives, which allowed us to find the slope, the instantaneous slope of a curve along pretty much any given value of x. And now we're going to find the area along a plane region between, to begin with, between the x-axis and a function's graph. Pretty cool. Okay, so as far as sigma notation goes, which this sort of E letter here is the Greek letter sigma, is the sum of n terms a sub 1, a sub 2, a sub 3, up until you get to a sub n. And it's written as sigma, or the summation of a sub I, as I starts at 1 and goes up to n, is equal to a sub 1. We're just going to take this lower limit, or this lower value, plug it into this expression, write it out, and then increase it by 1, plug it in, write it out, increase it by 1, plug it in, write it out, each time adding those resulting expressions until we plug in the upper limit and get the last term in that sequence of additions. If you've been watching my videos along my calculus list of calculus videos, I have a video posted where I really do some more basic type skills with the sigma notation, and so you can watch that if I breeze through this too quickly. The letter I is our index. We have a lower limit, which does not actually have to equal 1. We're just going to be using a lower limit of 1 as we use these four formulas here that we'll use in the remaining, or the subsequent examples. We have a lower limit and upper limit. We do count by 1, only by 1. Doesn't have to start at 1, but the lower limit can be 0, can be 3, can be whatever, but it has to go up by 1 until we get to the upper limit. And this is considered our ith term. So what does that mean as just at least one really basic example? The summation of 2k minus 1, where k starts at 3 and goes up to 5, is simply written like this. It's going to be, whoops, left my focus symbol there. It's going to be 2 times 3 minus 1, and then we're going to plug in 4, so it'll be 2 times 4 minus 1, and then we're going to plug in 5, and 2 times 5 minus 1. And the ultimate answer is, after we plug in our values of 3, 4, and 5, our lower limit was not equal to 1, we're going to just work that out and add all that up and get whatever the final answer is. Properties of summation. We're going to use these properties along with these formulas to do our examples here in a minute. If you take the summation of a constant times sort of like a mathematical expression, some like real math operation here, we can take that constant and move it out front. And so the summation as I starts at 1 and goes to n of k times a sub I, that ith term, we can take the constant and move it in front of the summation symbol and just write k times the summation of I, where it starts at 1 and goes to n, of a sub I. That step is not necessary for this kind of question where it's all arithmetic, but again, with the type of examples we're about to do, along with these formulas, we need to know how to do that, or that we can take that constant and move it out front. If we've taken the summation of two terms being added together, we can do the summation of each of those individual terms, get those overall answers, and then either add, or, this works for subtraction as well, we can subtract them. Okay, we will use these properties, which I'm now standing in front of, to manipulate our problems to allow us to use the following formulas. These are sort of like shortcut formulas. And you should have visited these in pre-calculus, or maybe sort of like an advanced algebra 2 course, possibly, if you were studying sequences and series. They're sort of just shortcut formulas to allow you to quickly do some of these summation problems. They don't always fit these patterns, but if they do, they're a nice shortcut. The summation of c as I starts at 1 and goes to n is equal to that constant times the upper limit of n. The summation of I as I starts at 1 and goes to n is equal to, now notice this n is the variable used in the upper limit, so it's equal to the upper limit times the upper limit plus 1 divided by 2. If it's the summation of I squared, again starting at 1 and going to n, it's the upper limit times the upper limit plus 1 times the 2 times the upper limit plus 1 divided by 6. And then finally, if you have I to the third, then it's going to be the upper limit squared times the upper limit plus 1 squared, make sure you lock that in the parentheses, divided by 4. So you're going to see basically what we want to do is, in these subsequent examples, is we're going to use these two properties and these formulas to do some questions like this one here, but instead of, we will be starting with the lower limit of 1, but instead of having a specific nth value, we're going to allow these to go to infinity. You'll see why we want to do that in the next video when we start finding the areas of these plane regions. For now, it's just strengthening our skills, and this video would be even longer if I try to explain exactly why we want to let that upper limit go to infinity. But we are just practicing our skills for the next video. So let's get these examples up here. Here's our first two examples. I got one up here. This is going to be a big one. And this little one here, I just want to show you with some, everything with like real numbers, the use of one of these formulas. So we have the summation as I goes from 1 to 10 of 3i. And instead of just doing 3 times 1 plus 3 times 2 plus 3 times 3 plus 3 times 4 and so on, let's actually use one of these formulas and see how they work. Well, none of these formulas have 3i. They have I squared, and I cubed. So we're going to take this 3, that constant, move it out front. That's going to be equal to 3 times the summation as I goes from 1 to 10 of just I. And now that we have this summation in exactly the same format as this first formula, we can use it. So it's going to be equal to 3 times, okay, let's see here, for the summation of I, it's the max upper limit times the upper limit plus 1 divided by 2. So it's going to be, my upper limit is 10, so it's going to be 10 times 11, because added by 1, divided by 2. That becomes 3 times 110 divided by 2. That becomes 330 divided by 2. And let's see here, there's 1, 2, and 3. That leaves a remainder of 1, 13. There's 6 2s and 13. And that leaves a remainder of 1, and that's 10. So 10 divided by 2 is equal to 5. So there's my overall sum. It's 165. Okay, let me pause. I don't want to run out of room. Let me pause and get this erased. For our next example, we have the question says, evaluate the summation notation for values of 10, 100, and 1,000. So instead of basically doing this exact same question 3 times and showing all that work, I want to do a little manipulation to this so that I can really quickly get all 3 individual answers after I do quite a bit of work in the beginning, and then the questions will finish up quickly instead of doing 3 completely separate problems. Another reason for doing this process I'm about to do is because it's going to be necessary for the next example, where you see how I'm letting my n get larger and larger? We're going to let that go to infinity. Remember I said we're going to incorporate our use of sigma notation with the idea of limits. And so right now I'm going to do this process for convenience for this question, but that'll build up the skills that we need for the next question. I want to rewrite this so that I do not have the variable I in the summation notation. I'm only left with the variables of n, and actually my final expression isn't even going to have a summation notation. So what do we want to do? Well, the first thing I want to do is I want to recognize that first property that I showed you, where if we have any kind of constants that we can pull that out front. Well, in the numerator, both of my terms have a value of 3, so I can factor that out. So we have the summation as I goes from 1 to n of 3 times I minus 1 over n squared. Now, it may not seem like it, but n squared is also a constant. The reason why is because the only value this is ever going to take on is the upper limit that we have in the summation notation. Now, it is identified as n, but for the first problem it would be 10, for the next problem it would be 100, and the next problem it would be 1,000. So this really is a constant. It's a non-changing number. So the 3 over n squared is that k in the properties that I showed you. So we're going to pull that out front and write this as 3 over n squared times the summation as I starts from 1 and goes to n of I minus 1. Okay, so now within my summation notation, I have I minus 1. That's not quite what I have here in these three formulas. So remember, the second property was the summation of two terms being added or subtracted together can be equal to the summation of each of those individual terms added or subtracted together. So we're going to write this now as 3 over n squared times the summation as, again, I goes from 1 to n of I minus the summation as I starts from 1 and goes to n of 1. Woo! Okay. Now, we're almost ready to start, rewriting this without the, well, we are ready to start writing this without the summation notation. We have 3 over n squared in the front, and the summation as I goes from 1 to n of I is equal to upper limit, which is n for our problem, so n times n plus 1 over 2. So this expression is going to come out, and using my three formulas, again, it's n times n plus 1 over 2. Minus, now I don't have this rule up here, but remember we said if this is a constant, then the answer is just n times that constant when you write out the summation. The summation as I goes from 1 to n of a constant is equal to n times that constant. So n times 1 is equal to n. Okay, let's continue to clean this up a little bit. We have two terms here inside the parentheses, so let's write that as 3 over n squared times, well, let's keep this in factored format. We'll have n times n plus 1. We're going to need a common denominator if we're going to add these, so let's put this n over 1 and multiply the numerator and denominator by 2. So we have 2n minus 2n over 2. Okay, now you can do these problems in any order you like as well. A little bit of flexibility in the order that you do the problems. I'm avoiding multiplying these together because I know what's ultimately going to happen is one of these n's are going to cancel out for a couple reasons. I just worked out the notes before I started the video. And see, this term has an n in it, and this term has an n in it. And we are multiplying, or dividing actually, by n squared, or multiplying by 3 over n squared. So this n is going to be able to cancel out some of those. So let's write that. Just showing you all the steps, maybe too many. Unless you're really struggling, then I hope it's helping. We're going to take an n out of these two terms and have n times, well, if I have this term and I factor out n, I'm left with n plus 1 minus 2. Now this term has an n, but I'm factoring it out front, so 2n divided by n is equal to just 2 over 2 from that denominator. Now this n is going to cancel out with one of these two n's down here. We have 3 times n, let's see here, 1 minus 2 is negative 1, over 2. And let's go ahead now and finally distribute that 3 and get 3n minus 3 over 2. Okay, now that was a lot of work, but what it allows me, I'm just making sure I haven't made a mistake here. What it allows me to do, though, I've forgotten something. Oh, I forgot my n. Whew, that was close. So what it allows me to do now is with this expression, if I want to evaluate this original summation notation for the values of 10, 100, and 1,000, I'm able to use this expression and get done just like that. So when n is equal to 10, we get 3 times 10 minus 3 over 2 times 10. That's going to be 30 minus 3, which is 27, over 2 times 10, which is equal to 20. And that decimal comes out to be 1.35. If I want to evaluate this expression or this original summation notation, it's in simplified form or just a different form. For 100, we have n equals 100. That's going to be 3 times 100 minus 3 over 2 times 100. That's equal to 300 minus 3, which is 297, over 200. And that is equal to 1.485. And then finally for 1,000, we get 3 times 1,000 minus 3 over 2 times 1,000. Of course, that's 3,000 now, minus 3, which is 2,997 over 2,000. And that comes out to be 1.4985. Okay, so we have the summation notation. We are letting I go from 1 to n, and we're letting that upper limit go from 10 to 100 to 1,000. And as you can see by my answers here, and look how quickly that went, even though I had to do all this preliminary work, our overall sums really are not increasing very much. Think back to when we talked about, well, this isn't necessarily just a geometric series, but in the sum of infinite geometric sequences or series, and that, if we met certain criteria, if the absolute value of r was less than 1, that the overall sum, the infinite sum, had, an actual limit. It had an answer. Even though we added indefinitely, the overall sum was approaching an infinite sum. And that's what's happening here. When n equals 10, it's 1.35. We let it go all the way up to 100. It grew a little bit. And then from 100, we added another 900 and gave an upper limit of 1,000, yet my overall sum didn't really increase by very much. So it seems like as n is getting bigger, as it's approaching infinity, my overall sum is also approaching its own limit. So that's where in the next example we're going to take a look at tying together our sigma notation with our new idea from calculus of limits. I paused the video because I didn't think I'd have enough room left to finish my concept here, but I do. You will have examples in your book that give you summation problems like this, and it will be asking you to evaluate, I'm sure, these ever-increasing values of n. But really, for us to ultimately be able to start finding the areas of a plane region, we need to know how to allow that value of n to approach infinity. So what I've done here in green, I didn't think I was going to have enough room, but I do. I've reworded the question now, and I'm going to let n approach infinity right off the bat. That's going to be the problem, evaluate the infinite sum, for 3i minus 3 over n squared. Now, to do this question in this format, you have to go through this process that I started with this question of basically expanding the expression, moving the constant outs, and using the properties of the summation symbol to get to a point where I can use these summation formulas to ultimately get some kind of expression with just n's in it and not have any summation symbols or sigma symbols, and not have any values or variables of I. So we've already done all that work, and we know that, we got the expression of 3n minus 3 over 2n. Now, including this limit notation now that we've learned in calculus, we can take this old skill that we knew from pre-calculus and just simply do this. We're going to rewrite this so that we have a bunch of small separate terms, and we have the limit as n approaches infinity of 3n over 2n minus 3 over 2n. Now, in our first term here, these n's, pardon me, very sorry for the interruption. So, these n's are going to cancel out. Now I have the limit as n approaches infinity of 3 over 2, and the limit of a constant is that constant, because we can apply the limit to each of these terms, you know that now. And the limit of 3 over 2n as we let n go to infinity, well, this is going to approach 0. So, the limit as n approaches infinity of 3 over 2 minus 3 over 2n is going to be 3 over 2, which is equal to 1.5. And hey, guess what? 1.35, 1.485, and then finally 1.4985. Gee, what do you think these are approaching? Now, let's see here. This isn't the easiest of concepts here, right? And I had to do a lot of work. So I'm going to do one last example, or at least put one more example up, get out of the way, pause the tape. Hopefully you can practice it on your own, and then I'll reveal the steps of the problems as we go, and I'll just be off to the side and kind of reveal the solutions as we go. So if you would like to try this on your own, you can pause the video in between each individual step if you're struggling, or maybe you can just get the solution right off the bat. So I got one last example, which I'm just going to reveal as we go along to finish the video. Thank you very much for watching. I hope this is helping. Here's the last example I'm going to reveal for you. We have a limit as n approaches infinity of the summation of I plus 1 squared over n cubed, where I starts at 1 and goes to n. Now, I'll be honest with you. I've been teaching 17 years at a high school level. I have a math education degree. However, now that I've developed this YouTube channel, and thank you for watching, I'm strengthening my own calculus and higher math skills, my upper level math skills, as I make these videos, because I've never had the opportunity to teach calculus, in my school or over the 17 years of teaching high school. So I am strengthening my own skills and using my own questions to develop these videos for you, which of course I do hope they're working and helping. That being said, I tried to do some little fancy substitution to make this numerator simpler and adjust the limits on my summation symbol, my sigma notation, and I kind of messed it up a little bit. So I'm just going to, keep it simple. Maybe I'm doing a couple more steps than I really need to, but I'm going to keep it simple. I'm just going to expand this I plus 1 squared, do some algebraic manipulations, and get to the right answer. So I'm not going to try and do anything fancy. I'm just going to do it, do the problem out the best way it works for me. It's quite a number of steps, though I don't think you can really avoid that with any of these problems. They tend to be extremely long. So let me get out of the way, pause the video, let you try this out, and I'll reveal the solution as we go. Thank you very much again for watching. Bam! I'm Mr. True. Go do your homework.